We're going to start by opening up to our purple divider, and we're going to write in topic 2, which is solving proportions. Yesterday we reviewed what a ratio was, how to create equivalent fractions, and how a rate usually involves time. Today we're going to learn what a proportion is and how to solve one. All right, then next you're going to flip over to the page that you've just glued in on solving proportions. So yesterday we reviewed what a ratio was, how to find equivalent fractions, and learned what a rate was, but we didn't really use the word proportion at all. Today we're actually going to talk about what a proportion is and how you solve one. So what is a proportion? A proportion is made up of two equal ratios or fractions. The way that we're going to write them, they're going to look like two fractions, but it's made up of two equal ratios. To solve a proportion, you need to find the missing value in one of those ratios. So you will know three of the numbers. There will be four numbers total because you'll have a numerator and denominator in the first ratio and a numerator and denominator in the second ratio. Of those four numbers, you will know three of them. So you're going to have to find the fourth number. So a couple different ways that you could go about actually solving the proportion. First of all, you could start by treating it like two equivalent fractions, just like we did at the start of our notes yesterday to determine whether or not our ratios were equivalent. So we looked at whether or not there was like a number we could multiply or divide both the numerator and denominator by to get the second fraction. We're going to treat it much the same way. So whatever you do to the numerator, you would also have to do to the denominator and vice versa. Ooh, this should say denominator. Okay, so in number 1, okay, it's asking me to solve for x. In number 1, I'm going to look at the two numbers that I know. For instance, I have both of my denominators here, but only one of my numerators. So I'm going to start by looking at the denominators, and I'm going to figure out what is that relationship between the 6 and the 42. If I'm dealing with a proportion or proportional relationship, I'm only dealing with multiplying and dividing between these two numbers. I'm not looking at adding or subtracting because that would be an additive relationship. This is strictly a proportional relationship. So if my number's getting bigger, that means I'm going to be multiplying. So I have to figure out what I'm multiplying 6 times to give me 42. This is where your times tables are helpful, so you can recognize if you multiply 6 times 7, that would give you 42. So I would have to do the same thing to the numerator. So I'd have to multiply 4 times 7, and whatever that is, which 4 times 7, that would give me 28. 28 would go in the spot where x is. So that means that x is equal to 28. We're going to take the same approach in number 2, except for this time I know both of my numerators. So I'm going to look at how I go from 25 to 5. So to turn a 25 into a 5, my number's getting smaller, so I'm going to be dividing. So I have to figure out what I'm dividing by. So 25 divided by 5 would give me 5. So if in the numerator I'm dividing by 5, I would have to do the same thing in the denominator. I would have to divide by 5. But I have to figure out what number, if I divided by 5, would give me 2. So again, those times tables are going to be helpful. So I know that if I take 10 and I divide that by 5, that would give me 2. So 10 would fit where the x is. That means x is equal to 10. Going on to number 3. The two numbers I know are in the denominator, so I'm going to see how does a 20 turn into a 10. It's getting smaller, so I'm dividing by, in this case, 2. So I would have to divide by 2 in the numerator as well. So I have to figure out what number divided by 2 would give me 3. Well, 6 divided by 2 would give me 3. So since 6 would fit where the x is, that means x is equal to 6. And our last example here, I know both of my denominators, so I have to figure out how a 25 would turn into a 100. I know that 25 times 4 gives me 100, so I would multiply by 4 in the numerator as well. So 5 times 4, that would give me 20, so 20 would go where the x is, so that means x is equal to 20. Now, sometimes it's not as obvious. There's not a clear factor that you're multiplying or dividing by. And we ran into that same issue with yesterday's note, where we had to determine whether or not two ratios were proportional. If we couldn't find a clear number to multiply or divide by, we used the butterfly method. We cross-multiplied. We're actually going to do the same thing here. If it's not obvious what you might multiply or divide by, you're going to use the butterfly method. For this method, you will first multiply to find the cross products. So that's where you're doing your cross multiplying. And then you will divide to solve the equation. So notice I haven't talked at all about an equation yet, but we're actually going to end up creating an equation when we do cross multiply. So you're going to cross multiply and then divide. That will be the pattern of how to solve our proportions if it is not a clear-cut pair of equivalent fractions. So in number 1, I have 5/12 is equal to 7 over x. Again, there's no clear way to turn a 5 into a 7. 7 is not a multiple of 5. So I can't just multiply 5 times something. So this is where I'm going to cross multiply. So I'm going to multiply x times 5, which I would just write as 5x. And then I would multiply 12 times 7. So this is where you do have Desmos handy and available. So you can just type in 12 times 7. That would give you 84. So 84 is my other cross product. Now, since I know that if this is a proportion, this is a proportion because I'm solving to solve for x, that means that my cross products have to be equal. So that means 5x has to equal 84. So now I just have a one-step equation to solve. So I'm going to box in my variable, draw my railroad tracks, and then to get rid of that 5, I would divide by 5, and then I would divide by 5, and x would end up equaling, if I take that 84 and divide it by 5, that gives me 16.8. There is no way on earth I ever would have figured that out just by trial and error. So cross multiply and divide, it's the best way to go, and it works every time. All right, number 2. Again, there's no easy way to turn the 8 into a 20. 20 is not a multiple of 8. So I'm going to cross multiply. So 20 times 3 is going to give me 60, and 8 times x will give me 8x. If this is a proportion, then by default, I know that my cross products are equal. So that means that 60 is equal to 8x. And it's okay that my x is on the right. We don't need to freak out about it. We're just going to keep it on the right as we solve our equation. So I'm going to draw my railroad tracks, box in my variable. To get rid of the 8, I'm going to divide by 8 on both sides. So I have x over here, and then on the left, I have 60 divided by 8. Again, this gives me another decimal, 7.5. Again, not an answer I would have been able to figure out without cross multiplying and dividing. All right, there is no easy way to turn the 15 into a 100, so I'm going to want to cross multiply. So 100 times x, I would write as 100x. And 15 times 30, when I work that out over to the side, 15 times 30 would give me 450. So my cross products are equal, so I have 100x equals 450. So I box in my variable. To get the x by itself, I'm going to divide by 100 on both sides. And dividing by 100 is the same as just moving your decimal point 2 places to the left. So if I have that 450, I divide that by 100, it would just be 4.5. So x is equal to 4.5. And last, in number 4. No way to easily turn a 4 into a 25, so I'm going to cross multiply. 10 times 4 would give me 40, and x times 25 is 25x. I set my cross products equal, so 40 equals 25x. To get the x by itself, I would divide by 25 on both sides. On the right side, I get x by itself. On the left, I would have 40 divided by 25, which is 1.6. So 1.6 equals x, or x equals 1.6.